Is this the same class? Is this the same class? Um, do you want me to finish that lecture? Okay, then yes. And do you want me to just go through both lectures no matter the time, or do you want me to go for 1 hour? Okay. Okay. Yeah, I do. Okay, so last time on Wednesday we were talking about weathering and erosion and the difference between the two, among all other types of things. Here is oh, I'm sorry. Let's see. Sorry. So this is my email. If you have any questions about the lecture or anything we go over, just feel free to let me know. Maybe I'll just kind of flip through these so you can see what we talked about. So the main difference between weathering and erosion is weathering is the breakdown of rocks into smaller pieces, and these are called sediments. Erosion is how the sediments are kind of moved away or transported from the original rock to different areas by wind, gravity, glaciers, man, running water. Hopefully we'll talk a little bit about man and our influence on erosion a little bit. And there's deposition, which is how are these sediments left behind? What way are they arranged, and how can we look at the way they're arranged and see what's happened in the past? So knowing these things is very key to knowing the history of the planet. So yeah, we kind of got through a lot of material last time, and don't be worried if you don't have all this material committed to memory or anything, but yeah, it's just important to know there's different types of weathering. This is
น้อง
some
ๆหน้าเว็
chemical
บอะ
weathering. This is where
พวกพี่กำลังอัปเกรดให้มันเป็นภาษาไทย
the
กับภาษาอัง
chemical
กฤษและภาษา
structure
ญี่ปุ่นได้ เดี๋ยวโพสต์จะกลับมาภายใน
of the
วันนี้
rock
เพราะ
is
ฉะนั้น
changed
ไม่ต้องห่วงโอเค
either by its exposure to oxygen, exposure to water, or exposure to carbon dioxide. Um, these are just some examples. There's probably 50 different ways of chemical weathering. These are just some examples. Surface area affects weathering. The more surface area, the more weathering is going to happen. If you have huge particles, they're going to weather slower than a bunch of small particles, and again, this is because of surface area. I'm just going through these pretty fast so we can kind of hopefully get through the whole lecture. I just want to revisit this so you're not coming in without knowing anything. Also other factors that affect weathering. How dense are the rocks? What are they made out of? Stronger rocks are going to weather slower. And what kind of climate are they in? So tropical, warm, moist climates have actually the most weathering. So areas like Thailand are very prone to lots of weathering because chemical reactions work well in warmer climates, and there's a good amount of rain, so there's a lot of running water, and erosion is pretty common. This is the soil profile. These are the different horizons. I guess the important thing to take away from this is that soil is always arranged in some kind of layering pattern if it's not been disturbed very recently. So you have the top, which is like the vegetation, shrubs, sticks, moss, That's O. And here you can see this is not really a layer. So the topsoil, subsoil, and regolith. So you know, they have this kind of soft area where the roots are. This is where most of the nutrients are. And then this is kind of what you call like the bedrock. These are like where the boulders are and large rocks. These need to be broken down, you know, or submitted to the forces of weathering, and they'll kind of slowly either turn into this or be transported in some way. Transported soils, so we went through this. We went through this graph here. You can see that, you know, this is where glaciers are, strong mechanical. We talked a lot about glaciers last time. You know, some rocks are harder than others. You can see this white rock is clearly different type of rock than this red rock, and so it's going to erode much more quickly, and you get this kind of head looking rock. I mean, this thing is like, you know, 30 meters tall, and it's balanced on this small white band, and that's because this rock is much less dense. Yeah, we went through waterfalls. Shale is going to be easier to be eroded than dolostone. You get this lip that comes over and creates these waterfalls. The faster a stream is moving, the larger particles it can transport. That's this graph. We went over this last time. Mount Rushmore, the only reason to go to South Dakota. Went over that a little bit. Shale. So yeah, this is an important slide. We went over this last time, so I won't go over it in detail this time. But we have, you know, you can look at the landscape of an area and kind of try to determine how was this formed, and you know, if you see rounded, smooth, sorted piles of rocks, you know maybe running water had something to do with it. If you know that you know, small particles of sand look like they've eroded something, you know, maybe that's wind. You know, any of these are clues as to how this stuff was formed. Extreme wind erosion, it's pretty epic. This is pretty important because you know, a lot of erosion has to do with water in some way or another, frozen water, or just running water, and these are kind of terms that are used to describe the amount of solids that are being transported by water. These are the ones that you can't even see that are dissolved in the water. Suspension, they're the ones that make the water look really cloudy, and saltation, which is the kind of boulders that or pebbles and rocks that bounce along the bottom of the river. So yeah, we went over most of this stuff. If you're dealing with a steep slope, then you're gonna have more weathering, more erosion, because you know gravity's gonna be acting on this stuff more. The water that's running down the hill will be going faster, so it'll be able to transport larger rocks and other kinds of sediment. That picture didn't work, but we also, so this is where we talked about deposition, and this is pretty close to where we, yeah, so this is where we left off last time. So Oxbow Lakes, which are really interesting, they're formed by streams that are curved. Okay, so as you get a stream that's just a little curve like this, eventually the water's flowing faster on the outside, so it starts cutting away the outside of the corner, outside of the curve, and it starts depositing sediment on the inside of the curve because the water's slowing down. And you know, this very small effect over long periods of time creates this huge bend, and now this water on the outside is moving even faster than the water on the inside, and it creates this, you know, big thing. And eventually the water, it will be more efficient for the water to kind of go in a straight line, than to go all the way around. So it'll just cut this off and it'll turn into this. And then you'll have a little island here, and this island will have this kind of donut shaped thing of water, and then you have this river right here. So as this starts adding more to this bend here and this bend here, you kind of get this cut off, and then this portion of water is just completely isolated from the river, and that's called an oxbow lake. So here's the oxbow lake, and you can kind of see from this one that what could be this, if this just kind of cut off here, you'd have this big oxbow lake. These are just kind of examples of what we call watersheds. So that's a good term to remember. A watershed is just a area that water runs through. It's where a river or several streams, an entire flood plain would be considered a watershed. So this whole area here, this is it's important to know that rivers travel through different landscapes, and as this maybe dries up, you could walk along this dry river, and by the way the sediments are and the way the landscape is, you could kind of tell what has been going on there in the past. Okay, so this is man's influence. Okay, this is how man is influencing erosion. So forestry. The interesting thing about forestry is that when trees grow, their roots add structure to the soil. So if you take out all the trees in an area where there were a lot of trees, and then there's a lot of rain, that area will become weathered and erode extremely fast, much faster than in a normal environment. And that's what kind of causes these huge problems in places where there's flooding, but then there's no trees at all, because an area with a lot of roots, it can actually take and hold much more moisture than an area with no trees. Strip mining is basically when you dig gigantic ruts into mountains looking for kind of minerals or gold in order to get lots of money, and there's a big drive to do this because it's much faster than doing mining where you're worried about what you're doing to the land. But if you have this huge trench here and then it rains and you have all this sediment that's been broken down, it's just going to wash all this stuff away, and really it'll take nutrients from the soil and it'll move it. It'll also just cut into the mountain and start destroying it at a very, very fast rate. You could talk about each of these things for a really long time. I'm just going to kind of go over each one. Construction. So construction, you want to have these big machines doing work for you. If they work really hard to flatten out an area, because they have these big tracks on them, if you were to use a big tractor in an area that's used to absorbing water, it'll kind of create this really hard layer, and as the rain kind of falls on it, it'll just wash over the top of the layer as opposed to being absorbed. So it's important to know that when you use construction with large machinery, in a lot of areas it can compact the soil, which just means to crush the soil so that water can't get in, and that's really bad for plants and animals. Improper farming, same kind of thing. Also with improper farming, say you have a plant that should be grown each year. You can use the same plants to grow the food each year, but you want to get more of your product, so you take out all the old plants and plant all new plants. Every time you take out all the old plants and plant new plants, you're taking out more nutrients from the soil and kind of just throwing them away. So this is a way that you can kind of erode and get rid of good land and create bad land is through improper farming. You take nutrients out of it over and over again, and pretty soon you can't use it at all to grow food. Salting highways. The salt can combine with other minerals and create chemical weathering, like we talked about before. If you use a lot of salt, it can really harm the environment. Not to mention, when you're driving your really nice car on a salted highway and the salt kind of splashes up onto your car, it erodes your car. It's gonna be pretty bad for the bottom of your car. Okay, so deposition, which is kind of the third step. So we have weathering, erosion, and deposition. So deposition is the process where sediments are released or dropped by their agent of erosion, and we can kind of think about this as, after they're transported by whatever agent, how are they kind of released from being transported. So if something is inside of a glacier, in what way is it dropped out of the glacier? And most deposition happens in standing still bodies of water, so oceans and lakes. So say you have a big river and it's carrying all of this sediment. It's got the dissolved sediments, and then it's got the clay it's transporting in the middle of the river, and then it's got the rocks bouncing at the beginning. When it hits a large body of water, like an ocean or a lake, it's going to slow way down. And when it slows way down, all these things are going to drop out of the river. They're going to be floating along in the river because the river's moving, and then they're going to hit the lake or the ocean and drop down. So this is really important. Deposition is caused by slowing down of the agent of erosion. So it's important to know, just like with the Oxbow Lake, when the water slows down, sediment is falling out of the water and it's being deposited onto the river bed or onto the sides of the river. So 3 factors influence the rate of sediment deposition. You have sediment size, sediment shape, and sediment density. So can anyone tell me why sediment size would affect rate of deposition? If something is large, what will that affect the rate of deposition? If something's really big, the water needs to be going really fast to kind of keep it from being deposited. So if it slows down a little bit, then this is just going to fall out of it. So the larger a sediment is, the faster the rate of sediment deposition is. So if you have, it's the same, it goes for these other two. If you have a really dense sediment, if it's heavy, it's going to fall out of the water. It's going to fall out of solution faster. The shape, so if you have a really round rock, it's going to be able to bounce along the river bottom. But if you have a really flat rock, it's not going to really be able to roll very well, and it's going to really easily be deposited. So if you have tons of flat rocks, the rate of deposition is going to be really big because these aren't going to want to stay in their agent of erosion, unless you're talking about a glacier. But if you're talking about a river, these guys are not going to want to stay. Okay, so density we just talked about. If something's heavier, it's going to drop out faster. Okay, so this part's very important. If you graded bedding versus vertical sorting. Larger particles settle on the bottom and smaller particles settle towards the top. This happens naturally when a fast-moving river meets a large standing body of water. The velocity of the lake water decreases quickly So a perfect example would be a waterfall falling into a lake. So you have this river, it falls off a cliff, and it lands in this lake. So everything just slows way down. And what's going to sink to the bottom first? You know, these huge rocks are going to sink to the bottom first, and then, you know, following suit, all the smaller rocks, and then the smaller rocks, and then the smaller rocks. So if you dig, you know, if you just take a chunk of the bottom of a lake where a waterfall is falling into it, this is what you'll find. You'll find a layer where there's huge rocks on the bottom, or, you know, the largest rocks are on the bottom, and the smallest rocks are on the top. And then, you know, after you get to the biggest rocks, then it'll start over again, and you'll find little rocks and then big rocks, because sediment, they're always organized in these layers, and each layer kind of represents an event. So say upstream of the river you have a bunch of rocks that fall into the river from a mudslide or a flood. You have a bunch of rocks go into the river, and then the rocks get pushed off of the waterfall and then fall in this pattern. They're going to organize themselves in this way, and then you're going to kind of get another event that happens maybe similar to that, and so you're going to get layers of these events. So you can kind of see here, each layer of graded bedding represents a single event of deposition. So this is one event of deposition. This is not an event of deposition. This whole thing is an event of deposition. Within a single layer, the particles gradually change from largest at the bottom to smallest at the top. So, you know, this or this, whatever you prefer, you're going to have the biggest rocks on the bottom and the smallest on top. So yeah, who cares? What's the deal with this? Okay, so the big ones are on the bottom and the small ones are on the top. That's obvious, but it doesn't always happen like this. And we know that if we see this, then we're in an area where there is a waterfall, or where there used to be a waterfall. So again, this gives us some insight into the history of the landscape. We know what was there before. Say the lake has dried up and so has the waterfall, we'd still know that there was a waterfall there at one point. This is, like I said, you know, it doesn't always happen vertically. Yeah, just, I guess, so you know. This is vertical sorting. This is a keyword you should know. Vertical sorting happens with waterfalls. Big rocks on bottom, small on top. This is called horizontal sorting. And this is where moving water enters a larger, still body of water slowly and causes larger particles to deposit closer to the shoreline. So this fast river kind of hits this big lake and slows way down. Slows way down. And the largest boulders kind of stop. As soon as it slows down, they just kind of get left behind right here. And then, you know, as it slows down, it can only transport smaller and smaller particles. So at the furthest out from where the river comes in, you'll find the precipitates, which are the dissolved particles, the clay, then the silt, and then just consecutively bigger. And you can kind of picture that. It's the water's moving really fast, and then hits this huge body of water, slows it down, and we know that the faster the water's moving, the larger the particle that can be carried. So obviously the largest particle is going to drop out first, and you get this arrangement. So say again this lake dried up completely, we would know that since there's big boulders near the edge of it and the whole bottom is clay and stuff like that, that maybe there were several streams running into this river, or you'd know what direction the streams were coming from, or any kind of information you'd want about which the stream and the size of the stream and where it was coming from. You could tell from this kind of diagram. Okay, so I don't know if anyone can recognize this formation. this is in Egypt. This is the Nile. And a delta is a fan-shaped deposit that forms at the mouth of a river when it enters a large body of water. Okay, so this kind of gigantic river, the Nile, and I don't remember where, it's one of the biggest rivers in the world, definitely. I can't remember if it's the biggest or whether I can't, well, I think it's one of the biggest anyway. It's this gigantic river, and when it's moving into this large Mediterranean Sea, it creates a delta, and it basically fans out in this huge area. And what this creates, the Nile Delta, is a ton of really fertile land. This stuff is very, very rich in nutrients because as it hits, the sediments are being released. The water's slowing down, it's spreading out, and all these things are being released. And precipitates, the stuff dissolved in the water, include very, very vital nutrients to growing plants. So, you know, if you need nitrogen, you got tons of nitrogen here. You have all these wonderful elements that this is the most, if you wanted to build a farm in Egypt, which, you know, maybe you do, maybe you don't, I don't know, but if you ever get the idea, you should definitely build one near the Nile Delta, because that's where the soil is going to be the best, and you're going to get the most products. This is like a picture view, like a drawing, and this is a actual photo from space of the delta. So this is much more rare. This is an alluvial fan, and it's basically when a river kind of spreads out over a area of land that's flat. And this kind of generally only happens when you have seasonal flooding, or areas where you're having tons of erosion in these valleys and the water is carrying it, and then it creates this fan, and then it dries up until the next time it rains, and then it floods again, and does this over and over again. And this is sediment. This is usually less nutrient rich just because of the areas where this happens. But sometimes, like in desert environments, you'll find alluvial fans. It's called a land delta. So yeah, this, the main difference between an alluvial fan and just a delta, like in the Nile, is that this is water hitting land, not water hitting water. Okay, so this is really fascinating. Cross-bedding is a situation where layers of sediment are deposited at angles to one another as a result of a change of direction of the erosional agent. So this may look pretty boring, but what you can't actually see from this is this guy is, I don't know, probably, I don't know, 6 feet tall, or, you know, average height, and this entire area, this is a deposition event, like we were talking about before, and it's angled kind of slanted like this, and then there's this clear border, and then you have this kind of totally horizontal stacking of sediments. And if you want to be fancy, this is called stratification, but you don't need to know that. But if you want to know it, that's the word. And you can see below him too, there's this kind of horizontal thing going on. And geologists believe, and there's a lot of evidence to support this, is that this just means that whatever was moving this sand changed. It either changed direction, or it actually changed what it was that was moving this. So you could say that maybe from here to here, you know, water was kind of doing this, or there was tons of dust storms. Something happened to deposit this in this angle. And then, you know, how long is this? Probably tens of thousands of years, hundreds of thousands of years. It depends on the rock and you know, the size of this layer, but this is definitely tens of thousands of years to make this one layer, and then whatever's lowest is going to be the oldest, and whatever's highest is going to be the newest. So just out of pure luck, this kind of whole area is exposed usually by either something kind of breaking this rock, this whole part off, so that this guy can stand here and be like, well, this is awesome. But really it's mainly you got this kind of change in angle, and you can see all kinds of examples of this in real life, and it's just really interesting to look and say, well, you know, what happened here to create this huge difference in the way that this rock was kind of put down. So I think it's pretty cool. That's the last slide for this lecture. I have one more group of slides, but yeah, hope you enjoyed it. Talk to you guys soon. So I finished the guys thing. Oh, we bought it from last night. Okay. Yeah, just sit down. Yeah. Okay. So this is the same rocks and minerals. The chemistry, or I guess, is this the same class? Yes, the same class. Okay. Right, yeah, I was gonna say, I was gonna skip that. This is the same class I taught the periodic table, yeah? Okay. This is more of like, they just kind of mentioned the chemistry, the geology, that's about. Alright, so we have about half time left, so this lecture, maybe you've heard some of the stuff we're gonna talk about, so hopefully we can go a little bit quicker and get through most of it. There's 91 slides on this lecture. Yeah, but it's not a lot of information. Okay. Okay. You can break up the you won't have to finish the slide, you know. Sure. This is material they need to learn this semester. Okay, okay. So we'll just get as far as we can in the time that we have. So. Okay. Okay, so rocks and minerals. This is just what we've been talking about. We're going to kind of talk about the difference between these two, which is pretty interesting. So matter is anything that takes up space. It can be classified in three ways. You have elements, compounds, and mixtures. We talked a lot about this in the previous one about the periodic table. So the smallest form of matter is the atom, and we kind of discussed that a little bit. We already talked about this. 109. This is just the periodic table. Yeah, smallest is an atom. So 2 or more atoms held by chemical forces is like H2O. If you want, you can review the other lecture on the periodic table a little more closely. It's got details about this. Yeah, we went over this: protons, neutrons, and electrons. Yep, water is a compound, H2O. Mixture, went over that. If you have a bottle full of hydrogen gas and helium gas, those are two elements. They're not bonded, but they're in a bottle, so that's considered a mixture. Chemical symbols used to write chemical formulas. So H2O is a chemical formula.
ม .1
It
พูดถึง
basically
อะไร ม
tells
.1 เริ่ม
us
ไปแล้วนะ
how many what atoms are
ม .1 เรียนไป
involved,
เมื่อ
what
เช้า
elements
นะค
are
รับ
involved, and how many of them. So
ก่อนม .2
H2O, the subscript, which we didn't
ไป
really
ดู
talk about
วี
this.
รันเอาแล้วกัน
H2O has 2 hydrogens
ใช่
and 1
เริ่มตอน
oxygen.
10
That's
โม
you
ง
can tell by the little
10
number
ด้วยมันอยู่ใน
2,
ตาราง
and
ที่เรา
sounds
โพส
pretty
ต์ตั้งแต่
simple,
วันจันทร์
but
แล้ว
sometimes you get into really complex compounds and stuff like that. So the subscript, the little number at the
ตาราง
bottom
ดีๆ
right
ครับดาวน์โหลด
is
ตารางกันไว้สิ
is
น้อง
very
ๆโพส
important.
ต์ตารางกันตั้งแต่วันจันทร์แล้ว
Okay, so mineral, which we didn't talk about before.
ใช่ไงก็เริ่ม
It's
11
naturally
โมง
occurring,
11
inorganic.
เราเริ่ม 11
It's got a chemical composition and a crystal
เข้าช้า
structure.
แล้วบ่นได้
We'll
ยังไง
talk more about that stuff. This is what it needs to be identified as a mineral. If it doesn't have one of these things, it's not a mineral. So inorganic, maybe you've seen the word organic before. Inorganic just means not alive. So it's non-living. It occurs naturally, which means we don't make it in a lab. And it has a definite chemical composition and crystal structure. So this doesn't mean that it's an element.
ไป
It
ดู
can be a
วีวันกัน
compound,
เดี๋ยวอัพโหลด
but
ให้
its compound
เดี๋ยววีวัน
is
เดี๋ยวตอนบ่ายๆเย็นๆวันนี้ก็ดู
it's
ได้หมดแล้ว
definite. So
ไม่ต้อ
it's
งห่ว
not
ง
really changing. If it changes, then the mineral will change by name. So
ตอนนี้
if you have a
เรา
mineral
กำลัง
like
อัปเกรดให้มันซัพพอร์ตภาษา
I don't know,
ไทย
pyrite is a
ญี่
good
ปุ่นกับภาษาอังกฤษ
example
ครับ
of a mineral.
แต่เดี๋ยววี
It's
วันตอน
fool's
บ่ายๆก็ดู
gold.
ได้
It looks like gold, but it's not really gold. It's made of sulfur and lead, but it's a mineral, and it has a crystal structure. We'll talk about that.
อีกหน่อยจะไปสอนหนึ่งญี่ปุ่น
So
นะ
here we
พี่
go. Inorganic, non-living, pretty simple.
อีกหน่อยระบบนี้ไปใช้สอนที่ญี่ปุ่นด้วย
They're always solid, which is interesting.
ไม่ต้องมีภาษาญี่ปุ่น
There's no liquid minerals. And usually their crystal structure, when they break apart naturally, they'll have a specific shape, and you can kind of tell what mineral it is by
จริง
the
ดิ
shape.
เด็กญี่ปุ่นเขาก็อยากเรียนกับครูฝรั่ง
Okay,
เหมือน
so
กับเด็ก
there's
ไท
a
ย
definite chemical composition. It can be made of a pure element, but it can also be made of a compound, 2 or more elements.
ใช่
Okay, crystal structure. So this is just a kind of a fancy way of saying that these atoms are arranged in a pattern when they're together with one another, and we won't go into the details of why that is, but it has to do with the structure of each element that's involved and their electric charge. So basically, when you freeze water, it kind of creates this crystally form, and water is just a unique compound that when it's liquid, it's not in a crystal form, but when it's solid, it is in a crystal form. Minerals always have a crystal structure. It's a repeating pattern. So say your material that you're studying has a crystal structure where there's 4 atoms arranged like in a square, and that's packed by another one that's arranged in a square. Or you have one that's a triangle, and then another triangle, and then another triangle. That's just the different examples of very simple crystal structures. There's 2,500 different kinds of minerals. So again, these are naturally occurring, inorganic solids with a crystal structure. So there's a ton of them, but they have this very specific, they need to meet all of these in order to be a crystal or a mineral. Okay, so these are some examples of minerals. These are kind of like, if you're into like gym show stuff, these are kind of you can buy these. They're all over the place. Pyrite is really common. Like I said, it's a combination of lead and sulfur to create this stuff that looks a lot like gold, but there are different ways to tell that it's not gold, and there's all different kinds. And yeah, as you can see, these are also different examples of crystal structures. So this thing looks kind of like a diamond. This has kind of a block square form, and this is what they look like in nature. They don't cut the minerals to look like this. This is how they take them out of the ground. They clean them off, and they have these crazy design patterns. This thing looks like it's just exploded and then frozen, while this kind of looks like a very organized geometric pattern. So yeah, this is just kind of another example of crystal structure, and minerals kind of have all of this stuff, and they can be just a simple cube, or they can be I don't even know what this would be called, a dodecagon or something. Actually, this is an example of pyrite right here. So you have these lead molecules in here, and then you have this sulfur out here, and it creates this very specific shape, and you can use the shape to kind of determine what it is you're dealing with. Okay, so where do these crazy shaped things come from? Most come from magma, which is the molten rock beneath the Earth's surface, where just below the Earth's crust. When it cools, mineral crystals are formed. So this is kind of where these compounds are isolated. They bond to one another in these crystal forms, and the extremely fast cooling kind of separates them from other things, which is why you find big, huge groups of crystals, different types of minerals together. What affects this? Well, how and where the magma cools determines the size of the crystals. When magma cools slowly beneath the Earth's crust, large crystals form. So this is like if you have something that cools instantly, you're going to have smaller crystals. If you have something that cools very, very slowly, you're going to have big crystals. So if you're looking for the largest diamond on Earth, you definitely want to look in a place where the magma has been cooling slowly, because if you really want that huge diamond that's gonna kind of make your fortune, you want to look in this area where it's being cooled slowly. So yeah, this is when it cools fast, small crystals form. So if you have two liquids, sometimes they'll be in solution with one another, and if they combine, they can form crystals as well. When the liquid evaporates or changes to gas, it leaves behind minerals and crystals. So it can kind of form these crystals. Generally, we call these precipitates in chemistry, but just know that sometimes you have these crystals that can form compounds in water or in other kinds of liquids, and then if you heat this up and get rid of the pure water or whatever liquid, it kind of leaves behind these crystals. Rock salt, perfect example. This is chloride compound that's left behind when you evaporate water, and it has a crystal structure. It's inorganic, which means it's not living, and yeah, it's a compound, so it's a mineral. This just talks about some of the most common elements. So out of 2,500, there are 1,000 that are common. 20 make up almost all the rocks in the Earth's crust. So oxygen in some form, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. And hopefully after the periodic table lecture, you guys know the symbols for all of these, and you're working on finding your having your homework passed taken care of. But actually the only one there's two of these that are confusing. Iron is Fe, is the symbol for iron, and sodium is Na. The rest of these, and potassium is K. So you're going to want to watch out for these three. But magnesium is just Mg, aluminum Al, pretty easy. But these three are kind of hard. But hopefully you'll be able to write these in the short notation, because it takes a long time to write all this stuff. You can write it, say O-S-I-A-L-F-E-C, whatever. Yeah, so mineral groups, right? We have these different kind of classifications, because there are tons, and we want to kind of break them down in these different groups. So it's not important. Don't feel like you need to memorize this. Just know that you have these different kind of groups. No one's really gonna ask you to recreate this complete chart or anything. I don't think, but you have silicates, carbonates, oxides, sulfates, and halides. And these are examples. Silicate, silicon. You have O2 as well. Carbonates, carbonate, and then you just remember you have calcium as well. Oxide, iron, sulfate, sulfur. Halides is kind of confusing, sodium and chlorine. But so these are the elements that make up the minerals, and this is the name of their classification. So yeah, like we said before, these minerals have these different ways you can identify them, and we saw in that photo those 6 different minerals. I mean, they're so different looking. They have different colors, different shapes, different amounts of shininess. Here we can see, color, luster, which means shininess, hardness, yeah, how shiny would be the luster. Hardness is just the density. It's going to be how difficult would it be to cut this thing. The streak is pretty cool. For pyrite, like we were talking about before, or fool's gold, a really interesting way you can tell that it's fool's gold is when you scratch it onto another surface, the color is silver. It's like a darker silver kind of color, and the rock itself is gold in color. So if you scratch it on something and it's silver, then you know it's not gold. And back in the day, if you brought a bag of pyrite and said it was gold, they would scratch it on something and be like, get out of here, this is fake gold. Hardness and density kind of go together. If it's more dense, it's generally going to be harder. The shape of the crystals, so we saw the one that looked like it was exploded and frozen, diamond, square, and the very ambiguous other special properties, which probably just means they have this machine called a spectrometer, which you can cut thin layers of the rock, shine light through it, and then when the light looks like on this side, you could tell what mineral it is that way as well. So if you're really into rocks, this is super interesting, because minerals are actually different from rocks, because they're all the same compound and they're in this crystal form, but they occur naturally, and they're generally really beautiful, really nice looking. Okay, so yeah, color. Some of them are orange, some of them are blue, purple, really bright colors. Depending on what kind of light you shine on them, some of them have different colors, which is really cool. So if you have a favorite color, I guarantee you will probably be able to find a mineral that matches that color, and you can go to the gym show, and depending what it is, you can cover your entire house with it. Some people do that. I don't know if that's common here, but my grandma is really into that. So yeah, this is looks kind of like sulfur to me, but it's yellow, and it's got this kind of blocky form. It's not really jagged. but this is color. Some minerals have different colors. So quartz is a really common mineral. You can pretty much find it anywhere. Even if you kind of pick up a rock and break it, in a lot of places there will be some quartz in there, and it's kind of this white crystal. But it does come in different shades. You have this dark shade, you have orange, you have this going on, and this kind of you need to know that even if something is a certain color, you can't necessarily say it's a certain mineral. You have to do multiple kinds of tests to see what actual kind of mineral it is. Yeah, so this is the way the mineral reflects light from its surface. So luster is basically shininess, and metallic luster just means they look kind of metally when you shine light on them. Silver, copper, gold. In the past, minerals with a lot of luster, metallic luster, were considered more valuable, which is why we have gold and platinum and silver and all this. They're more valuable because before we knew any of this geology stuff, people just looked at it and they liked it for some reason. People like things that are shiny. There are other ones that non-metallic. They look really dull. This thing, it's kind of glistening. It's kind of shiny. You have this is kind of reflective. Glassy, so quartz, is kind of glassy, looks kind of like glass. Pearly, dull, silky means kind of like opaque, cloudy looking. If you have the color and the luster, you might know a little bit more about it, but still that's not enough. This is an example of metallic luster. This looks like pyrite, and I don't know what that is. Really ugly mineral of some kind, but metally. Non-metallic. So this is anything that doesn't look like that. Non-metallic luster. So yeah, the ability to resist getting scratched. So if you have someone's going to sell you a diamond, and you see the diamond and you try to scratch it, and it makes a big scratch, from your penny or something, it's not a diamond, because diamonds are very, very hard. They're some of the hardest minerals. So if you see a fake diamond and you try to scratch something hard with it and it doesn't work, it's probably not a diamond, and you probably shouldn't buy it, unless you're looking for like a super bargain, or if it's like 30 baht or something. So Frederick Mohs, he's a famous mineralogist. He worked out this scale. Big surprise, 1 to 10. 1 is the softest and 10 is the hardest. So diamond is around 10, and I don't know what to be around 1, but you have certain, if you have the hardness, the luster, and the color. Sometimes you can say definitely what mineral you're dealing with. Yeah, Mohs scale, 1 to 10. So yeah, we talked about this with fool's gold or pyrite. The color of the powder scraped off the mineral when it is rubbed against a hard, rough surface is called a streak. So this is kind of the little breakdown particles of the rock. Generally, you need to streak something against a harder surface than the rock, so that way the rock is what's left behind, not a cut in whatever you're scratching it against. And yeah, this is a really easy way to tell what a certain mineral is if it's got a streak that's different than its color when it's reflecting light. So pyrite looks gold, but its streak is black, and it's very drastic difference in color. A streak plate has a hardness of slightly less than 7. So if the streak plate has a hardness of slightly less than 7, we know that most minerals are going to have a hardness less than 7. So if you get above 7, it's pretty hard. You're going to have to get a special plate if you want to do a streak on it. Usually you wouldn't, because these are above 7 is pretty rare, and usually it's going to be more valuable. This is just a very normal example. This is a streak plate, hardness of 7. This mineral would have to have a hardness less than 7, and it's got this red-brown streak, so it's hematite. You know, say definitely hematite. Okay, so we could do an entire lecture on density. It's really, really important. It's the amount of matter in a given space. So if something is more dense, the atoms are more closely packed together. So each atom has weight, and if you have more atoms in a smaller area, it's going to be denser. And it's kind of tempting to say that density is the same as weight, but that's not true. It's not the same as weight. It's just the amount of matter or a number of atoms in a given space. So this is an important property of a mineral. So the density is always going to be the same. Can anyone think of why the density will be the same of a mineral no matter what the size of the mineral sample? So if you had 100 kilograms of pyrite, it's going to be the same density as 1 kilogram of pyrite. Can anyone think of why that might be? So obviously 1 kilogram of pyrite is going to weigh a lot more than I'm sorry, maybe I said 1 kilogram. 1 kilogram versus 1 gram. So 1 gram of pyrite is going to be much lighter than 1 kilogram, but they're the same density. And if you're too shy to write on the thing, the answer is because there's this lattice structure. You have this structure of atoms, and the way that they're organized in the crystals, they're not able to become more closely packed together. They're fixed. They're kind of in these squares or triangles, and they cannot get closer together. So even if you have this gigantic amount, it's going to be the same density, which is the amount of matter in a given space. Okay, so the shape of the crystals. So if you couldn't tell, each slide is just a different characteristic of the mineral, and if you combine all of these and you find all of these about whatever, you could take any random thing blindfolded and test in these ways, and you'd know what mineral it was. The shape of the crystal is huge because you know if it's triangle, it can only be these. If it's square, it can only be these. If it's dodecahedron, it can only be these. There are 6 shapes: cubic, hexagonal, which is 6-sided, orthorhombic, monoclinic, tetragonal, and tetraclinic. So you need to know all of these by tomorrow. No, I'm just kidding. You don't need to know these at all. Just know that there are 6 basic shapes, and if you really want to look all these up, you can. If this is really, if that's important for you. But cubic is kind of self-explanatory. Hexagonal, same. These are very obscure. Just know that they're kind of organized geometric shapes, and they all contribute to the crystal structure and the different crystal shapes of different minerals. So yeah, we'll continue with this more later. Just what you really want to pay attention to is that to identify minerals, you need to look at their physical properties. So you don't need to have a huge lab for which is costs thousands of dollars to kind of find out what mineral you have. If you find a mineral and you don't know what it is, you can usually look up ways to test their what they really are, and you can actually do this at home if you have a streaking plate. You can't really test their density, but you can tell how hard they are, their luster, their color, their crystal shape. So maybe if you find a piece of a chunk of gold and you really are convinced it's gold, and you're about to like go quit your job and be like, I'm rich forever, and then you do a streak and it's black, you're gonna know it's just fool's gold and it's not worth anything. Don't make any rash decisions. So this could really save your financial career when the time comes. So pretty important. Hope you've enjoyed the lecture. I'll talk to you guys later. Okay, bye.